morning. In today's class, we will consider the explosions involving storage vessels which contain cryogenic fluids. We will also consider something on rupture of pressure vessels after we deal with explosions involving the cryogenic fluids. But to come back to the particular point of, let us say, explosions involving cryogenic fluids, let us say, we must first define what a cryogenic fluid or a liquid is. You know, any liquid which has its boiling temperature under normal atmospheric conditions less than minus 150 degrees centigrade, that is equal to 123 Kelvin, is called as a cryogenic liquid, or it is also known as a cryogen. You know, we find these cryogens are important not only as a fuel, like hydrogen is a fuel, maybe LNG is a fuel. It is also used for several other applications, and in the industry these cryogens are used. And we would like to understand what are the types of explosions which take place when they are kept in a storage vessel. Like for instance, let us say I want to keep a cryogen in a storage vessel. Apparently, you know, this is the cryogen, and we say cryogen is a low temperature fluid. That means its boiling point under atmospheric conditions is less than 123 Kelvin. Well, the vessel has to be insulated, very well insulated. Let us say it is insulated using, let us say, a double wall construction with vacuum, or let us say with several other, maybe foam, maybe you have multi-layer insulation and all that, such that you like to prevent the heat from the ambient. See, the ambient is something like, let us say, at 35 degrees centigrade. The fluid here is at temperature less than, we say, minus 150 degrees centigrade. Therefore, there is always a tendency for heat to flow in, and therefore you give sort of a good insulation, multi-layer insulation, vacuum insulation, maybe some powdered insulation, maybe some puff insulation, and so on. And therefore, let us say this is it, the vessel is very well insulated. Now, even if you give the best possible insulation, there is always some heat in leak which occurs. There is always some heating which is going to take place. You know, maybe it's small, but still it is there because of the large temperature differences. And what does this heating do? It causes, maybe, you know, when I heat this particular surface over here, little bit of heating, maybe the fluid becomes less dense over here, because whenever I heat a fluid, it tends to become less dense and the fluid sort of rises up. Here it rises up, and therefore you have something like the fluid which gets heated in the wall region tends to rise up because it is lighter in density compared to the original fluid, and it sort of accumulates at the surface. Therefore, you have the convective currents over here which go and cause the current to go like this, and you have the migration of the heated fluid which is less dense, and you ultimately end up with something like a lighter fluid on top, maybe lighter fluid on top, and maybe the heavier fluid at the particular bottom. Actually, the lighter fluid is at a slightly higher temperature, and with respect to time, what is going to happen is you have something like lighter fluid at the top, the heavier fluid at the bottom, and this process of having, because of the heat in leak which takes place, and in any vessel, however well you insulate, there will always be some level of some small heat in leak. It heats the liquid, and you have this process which is known as stratification. In other words, the lighter fluid comes to the top, it's little warmer, and therefore if I were to now plot the temperature gradient, if I were to, let us say, plot the temperature gradient over here, what I observe is, yes, well, at the top I have temperatures which are slightly higher, temperature which is slightly higher, maybe on this scale I plot the temperature, and then I have the temperature lower. That means I have a warmer fluid on top resting on a relatively lower temperature cryogen. You know, this is not only true for cryogens, it's also true, you know, at home. If I have, let us say, a bucket of water, and I put something like a heater coil in this particular water, I heat the water, what is it we observe? We find that when the water is heated, on top of the water, you have hot water at the top for quite something. In fact, you will find boiling of water takes place, but the temperature of water in depth is going to be smaller. This is also the same thing like stratification. Maybe the less dense water, when it is heated, water when heated gets lower in density, it rises to the top, and you have the warmer layer at top, which is called as stratification. Therefore, we find, well, you have stratification warm layer, and therefore what is going to happen? The gas, that is the vapor of this particular cryogen which is on top, is also warm at this particular temperature. It tends to be in equilibrium, and if the more and more warmer fluid comes over here, well, gas is generated, and therefore in all cryogenic appliances, you give something like a vent valve through which, if the pressure increases, well, the vapor gets lost, gets released through this particular vent, and when it gets released, the pressure decreases, well, the temperature decreases, and you can also control the temperature, because once the vapor is released, the pressure decreases, the temperature decreases, this layer is in equilibrium with the vapor here, and therefore you have some equilibrium type of thing. But all said and done, you have to release the vapor in order to keep the pressure in a cryogenic storage vessel constant. Therefore, you have the venting of gases. Before coming to a particular problem, let's take a look at 3 or 4 cryogens which are used, and then discuss what are the problems. Is there any particular problem associated with storing a cryogen in a particular storage vessel, in a well insulated storage vessel? But as we keep saying, whatever be the type of insulation, there is always some heat in leak taking place. Therefore, let us put a few cryogens. Well, we can talk of liquid helium. Well, liquid helium as a normal boiling temperature at atmospheric pressure of something like 4 Kelvin. You could have liquid hydrogen. The normal boiling temperature at atmospheric pressure is 20 Kelvin. I could also think of liquid nitrogen, which has the normal boiling temperature at atmospheric pressure is 77 Kelvin. I talk of liquid oxygen, which is at 90 Kelvin, the boiling temperature. And the last one, I talk in terms of liquid methane, and the temperature, boiling temperature, is 111 Kelvin at the ambient conditions. Well, these are the 5 typical cryogens which are cryogens because their operating temperature is less than minus 150 degrees centigrade or 123 Kelvin. Now, if we store some of these cryogens in this particular vessel, and let us say if it is not totally pure, what do you mean by not being pure? This is an essential part of it. Like for instance, let us say I store LNG. If I talk in terms of liquid natural gas, and we have been considering this, we considered the LNG explosion at Cleveland, we said, well, we talked in terms of natural gas explosion at Ural, we talked in terms of the liquefied one which entered the gutters and caused the manholes to sort of rocket up or skyrocket. Therefore, when we talk in terms of LNG, and this LNG is an important fuel nowadays, it is transported all over the world in tankers. Not only that, it is also transported in pipelines, and therefore, and it is also stored. It is also stored in tanks. Like for instance, off Cochin Harbour, we get LNG, we then store it in huge tanks, and these tanks are again, as I say, well insulated with a vent valve, such that if you have vapor which is being formed, you occasionally vent it out, such that you have this. And what happens? Let's consider this LNG. LNG is from the gas fields, it is got as a vapor, and it contains not only pure, it is not pure methane, it consists 90% of methane. It also contains some other substances, and the other substances which contains are, in addition to methane, the formula should have been CH4, it also contains some ethane, C2H6, it contains some propane, C3H8, and also little bit of, let us say, maybe petrol, like for instance gasoline. Well, if I look at the boiling point temperatures, well, liquid natural gas is stored, let us say, as a liquid. It is stored as a liquid. We say, well, it also contains some impurities, and these impurities are all fuels, mind you. It contains some liquid ethane, it contains some liquid propane because the temperature is low, the temperature is of the order of something like 111 Kelvin, which I can say is maybe 273 minus 111, which is equal to something like minus 162 degrees centigrade, because it is below 0 degrees centigrade. At this temperature, maybe the ethane which is contained over here is also a liquid, propane is a liquid, but the boiling point of, let us say, methane is, we say, is minus 162 degrees centigrade. Of ethane, the boiling point is something like minus 85 degrees centigrade. For propane, the boiling point is minus 42.4 degrees centigrade, and for gasoline it is something like plus 69 degrees centigrade. Therefore, when I consider liquid natural gas which is stored in large quantities in all over the world, you have this LNG is not pure methane at this particular boiling point temperature at atmospheric pressure, but it also has other traces of, let us say, ethane, propane and gasoline. And therefore, what is likely? Let us consider the problem. Just I keep the LNG, cryogen LNG in a particular vessel, and since it contains some of these heavier constituents, mind you, C2H6 is heavier than methane, propane is even heavier, molecular mass is higher. Well, gasoline is something like maybe C20H something, therefore it is even higher. Therefore, when I store these things in a vessel, now I will remove the outer layer, I just say, well, I store the LNG over here. What is going to happen? The heavier constituents such as, say, ethane, propane and gasoline are all at the bottom because it is heavier. Therefore, maybe I say gasoline is over here, propane over here, and therefore the heavier quantities are at the bottom, and the lighter methane, which constitutes maybe more than 94%, is what is at the top. Of course, you have a vent valve over here, and if some because of we talked in terms of stratification, we said, well, the thing arises and I have a stratified layer on top. This is my stratified layer on top. Okay. Now, what is going to happen? It is not that heat in leak occurs only from the side walls, but heat in leak will occur also from the bottom. And therefore, when heat in leak occurs from the bottom, you already have a relatively denser, maybe ethane, propane, gasoline at the bottom, and therefore, whenever some little bit denser liquid is heated by heat in leak from the bottom, well, its density decreases, but when its density decreases for these heavier substances, its density could still be less than the liquid methane on top. Therefore, even though it is slightly warmer, it tends to still be at the bottom, because even though it is heated more than the liquid over here, more than the liquid methane over here, its density is still not less than methane for it to migrate up. And therefore, it continues to get heated till a particular time when its density, let us say liquid density of the corresponding heavier constituents, becomes less than that of the liquid methane, and therefore, you have higher energy or higher temperature over here because it is more than this, and this layer of heated sort of heavier constituents of gases is known as thermal overfill. Therefore, now we know when it gets heated because of the further heat in leak, well, it rises to the top, and sort of when it rises to the top, it mixes with the stratified layer, and this what we call as something like a rollover. That means the heated thermal overfill comes and heats the top layer, which is already a little warmer. But mind you, now the temperature difference here is quite high. It comes to the top, mixes with the stratified layer, and you get a discrete increase in temperature of the surface layer, and mind you the gas over here is at the original stratified layer temperature over here, and all of a sudden this increase in temperature is such that the vapor pressure of this is not in equilibrium with the pressure here. Suddenly there is a spurt in formation of a gas, something like a flash vaporization. And this flash vaporization, as we saw in the last class, it generates so much of gas that it is not sufficient, the vent hole is not sufficient to vent it away. With the result, the pressure increases rapidly and you have the burst of the storage vessel. Therefore, whenever we talk of explosions involving storage vessels holding cryogens, we talk of thermal overfill. That means the cryogen is not a pure cryogen. Maybe it contains some substances, some cryogens which are, or some other substances which are relatively denser, and they can get heated to a larger temperature before that density matches with the layer above it, and all of a sudden when it gets heated to a level wherein its density becomes equal or less than this, well, it rises up. We call this as thermal overfill. It mixes with the stratified layer on top, namely a rollover process in which thereafter this flash vaporizes because it is at a higher temperature and the bursting of pressure vessel occurs. Therefore, whenever we handle cryogens which are somewhat impure, you have mixture of some other substances which are there, such explosions are likely. But in the case of LNG, well, it is obtained as a mixture of some substances. It is not pure methane by itself, and therefore LNG has to be, the storage vessel has to be designed with care such that the thermal overfill and rollover will not cause an explosion. Having said that, it is also important that we talked of LNG on and off during the earlier classes. We find that, well, we have tankers in the ship which are designed to take this low temperature fluid across the different oceans. We have the LNG over here, and if by chance, let us say a ship containing the LNG leaks out, supposing there is a leak on the surface of water in a sea, then you have LNG which is being formed, and we said this is very dangerous. Why did we say it is dangerous? Because if LNG leaks over, let us say, the surface of the earth, because the LNG is very cold, it immediately cools the earth, and also maybe it flashes into vapor because its boiling temperature is very low. But when it flashes into vapor, it absorbs the latent heat from the liquid over here, and therefore the rate of evaporation comes down with time. Whereas if the spill occurs over water in an ocean, because of the turbulence of the ocean and also the convection movement of water below the convection of water which takes place, the spill continues to evaporate. You have a very copious amount of LNG, and therefore LNG requires some caution when we transport it by sea, or even for that matter, LNG being a cryogen, it has to be handled with care, and there are problems such as we say, explosion in pressure vessels holding LNG, and it has to be adequately designed to hold the additional pressure. Having said that, we were looking at the explosions involving cryogenic fluids. There is another instance or another phenomenon which can again cause the explosions in the storage vessels. Let us take a look. We said earlier that you have the storage vessel, you have the cryogen which is kept in a storage vessel. Now let us say I have a storage vessel like this, I have a vent valve, because whatever said and done, you cannot avoid the stratification. You have a stratified warm layer at the top, and this keeps on, the amount of stratified layer is shown shaded over here. This is the stratified layer, and therefore the evaporation takes place, and therefore you have to essentially vent off the gases, right? When you vent off, supposing there is a sudden vent of gases, and if you vent out the gases, what is happening? There is balanced gas because of the expansion. That means the pressure gets reduced, there is expansion. the gas over here cools down. When the gas cools down, well, you know, it is almost at the saturation temperature corresponding to this, and if it cools down, well, it is below the boiling point of the vapor at the particular condition of pressure over here, and therefore we expect when it cools down, it should sort of get back from the vapor, it must become a liquid. But the process of condensation, that means the vapor becoming a liquid, takes some time, and very often with sudden venting what happens is you form something like a metastable vapor, which is a vapor at a temperature less than the boiling point corresponding to this particular pressure. In other words, you know, it is tending to condense to the liquid, but it's still a vapor, and it is there as it is, and therefore when you have regions, cold regions over here, that is the walls which are cold, and therefore all of a sudden this metastable vapor cannot exist as a vapor, it is waiting to condense, and therefore all of a sudden you have condensation taking place, and therefore you have this condensation taking place of the vapor maybe near the surface, and any condensation, to condense, you know, you have to reject heat, and therefore the condensation has some heat, that means, and this heat which gets rejected can drive a shock wave. And such a shock wave driven by condensation is known as a condensation shock. We can readily show this on our Eugonio, namely I have pressure versus 1 over rho. The initial conditions corresponding to the cool down conditions can be shown by the initial conditions P0 and rho 0. And what is it, or let us say 1 over rho 0, because my scale is rho 0 here, I have P0 into 1 over rho 0. And since some heat is associated with condensation, I have something equivalent to a condensation process over here, which is, let us say, metastable, and when it condenses, I have heat which is getting generated. I can always form a shock with some particular velocity, and this velocity, the Mach number of the condensation shock, is in general small. It is of the order of 1.4. In fact, these are encountered in any process in which you have a rapid cooling of the vapor, like in a wind tunnel you have this problem, you could have it in the case of the storage vessels. But anyway, you know, you have a shock, and this shock will increase the temperature, will also increase the turbulence, will lead to more flash vaporization, and this could also be a cause for explosions of storage vessels. Therefore, we can summarize by saying, well, when we consider explosions of maybe cryogenic liquids in storage vessels, well, the thermal overfill and rollover associated with different constituents in the cryogen, and secondly, condensation shock could contribute to the explosion. Well, this is about the explosions of cryogenic storage vessels. Let's move to the next topic, which is, let us say, something similar. We say, well, why cryogenic fluids? You know, any pressure vessel can explode. Like for instance, I have, let's say, a compressor. The compressor is used to charge a storage vessel of air, let's say. I keep on supplying the pressure at higher and higher pressure. Well, by chance, if my regulation system is such that I pressurize it to a very high value, well, this storage vessel could just explode, could just rupture. Therefore, we would like to find out what is the energy release during rupture of a closed vessel. Now, to be able to do that, let's again formulate it. It's quite simple. We have done something similar earlier. Let us consider a storage vessel of, let's say, volume V. Let us say it ruptures at a pressure P0, and let us say the volume is also, let's say, V0 of this particular pressure vessel. Let us say that the thermodynamic properties of the gas are such that it has a specific heat ratio gamma. The specific heat ratio gamma is equal to Cp by Cv. We have been looking at it for the different gases, and we will find, well, gamma also plays a major role. Let this pressure vessel, which explodes at a pressure P0, let the ambient pressure be P ambient, let the ambient temperature be also T ambient, let the temperature here be, let us say, T0 corresponding to pressure P naught over here. You know, I want to find out what is the energy released in this particular rupture, and how do I say? Well, the energy released in this rupture, let us say E, is equal to the initial internal energy which is contained by the gas over here. Mind you, it is a constant volume explosion. Therefore, I say, well, the initial value of the internal energy over here minus the final value of the internal energy of the same volume here. And what is this equal to? This is equal to per unit mass. I have small u, that is so much kilojoules per kilogram, into the initial mass of gas, let us say, is m0 over here, m0 into ui, minus when the explosion has taken place, in the same volume I have final mass over here, and let us say that the internal energy is small uf, so much kilojoules per kilogram. Therefore, it is equal to mf minus uf over here. Therefore, I want to solve this. I am interested in finding out how much energy is released during the particular rupture, and therefore, let us put things together. I have E is equal to m0. You know, I can write internal energy. We have seen internal energy is equal to Cv T, that means T O, that is the initial temperature over here, minus Mi into Cv into the ambient temperature, because once rupture has taken, it is the ambient gas which is occupying this volume. Well, the final pressure is equal to the ambient pressure because nothing is there over here. We also have, well, Cp minus Cv is the specific gas constant, or Cv, I take it in terms of gamma over here, is equal to R over gamma minus 1, specific gas constant in terms of kilojoules per kilogram Kelvin, and therefore, I can write this as equal to m0 into R T0 minus I have Mi into I have R into T ambient divided by gamma minus 1. All what I have said is I have substituted Cv is equal to R gamma minus 1, and I take gamma minus 1 common in that particular denominator. And here the assumption made is gamma for the gases over here and gamma for the gases here is same, which need not be so. A high temperature gas has a lower value of gamma, as we shall shortly see. But when I look at this particular expression from gas equation, I have PV is equal to MRT, specific gas constant, and therefore I can write this MRT0 is equal to the initial value of pressure, let us say P0 is what is said is the pressure over here, into V, that is the initial volume, the volume does not change, we said that the volume is V0, minus the final volume is again V0, MRT0 corresponds to the ambient pressure over here, therefore this becomes P0 V0 minus P ambient V ambient divided by gamma minus 1, or rather the energy released, if I take V0 common because the same volume is there, I get V0 into P0 minus P ambient divided by gamma minus 1, which is the energy which is released during the rupture of a pressure vessel. If I say, well, this is there, I find, I find that, well, you have gamma, and for air gamma is 1.4. You find that small changes in gamma is going to affect the energy release. Therefore, let us take a look at gamma. What are the factors which influence the gamma? Because you find, well, it is not only the volume and the initial pressure, but it is also the value of gamma which is influencing the energy release, and therefore, let us see what gamma represents. In fact, if you go back and see the Chapman-Jouguet velocity for a detonation, we also got it as equal to 2 gamma square minus 1 into q. There also it was a strong function of gamma, and we found, well, gamma changes between the unreacted gas, reacted gas, we took it to be common, but here also it is sensitive to gamma. Therefore, I think it is necessary to be a little more clear about what are the factors which affect gamma. Well, let us say if I have something like a monoatomic gas, something like helium, let us say, it is a simple gas, it is just a gas which has let's say monatomic, it has only 3 degrees of freedom, it can move in 3 directions, therefore the degree of freedom it has is 3. If I take a diatomic gas like air, like I have nitrogen, oxygen, and which constitutes air, I say it is diatomic. Well, it is double, therefore it has 3 translational degrees of freedom. It can also rotate in 2 directions, therefore the degrees of freedom are 5. Therefore, if I keep on increasing the complexity of a gas, like for instance, I take something like, let's say, trichloro, some refrigerant, let's say, trifluoro, let's say methane, which is used as a refrigerant. If I consider this, it's much more complex, and the number of degrees of freedom are quite large in this case. It's of the order of something like maybe 10, 15 or so. And therefore, when I heat a gas, again, what I do is I increase the degree of vibration levels of the gas goes up, and therefore its degrees of freedom. That means I convert some of the energy into the vibrational modes of a gas, and if it is vibrational modes of the gas, the degrees of freedom goes up. If it is rotational modes, the degrees of freedom goes up. And it is possible to connect the gamma to the degree of freedom as, say, 1 over 2 by the degree of freedom. This comes from the kinetic theory of gases, and therefore you find that for monatomic gases such as helium, which has a degree of freedom of 3, it is equal to 2 by 3 is the value of gamma, which is equal to 1.67. For a diatomic gas, it is 2 by 5, which is equal to 1.4. And for a gas like trifluoromethane or difluoromethane, it is of the order, that is, gamma is of the order of around 1.1. And therefore, for a heated gas in which it's very hot, maybe the gamma will be very low. And when we talk of a low value of gamma, apparently in my denominator I am having gamma minus 1, therefore the denominator becomes a small number, and therefore the energy release goes up. Therefore, let's do a small problem to find out the sensitivity of the energy release in the explosion of a pressure vessel with respect to the value of gamma. Therefore, let's do this problem. Let's say I have a pressure vessel which holds, let's say, air whose gamma is 1.4 at a pressure of, let's say, 10 MPa. Let's say the ambient is ambient pressure is 100 kilopascal, which is 0.1 MPa. This is in the other case, and this vessel, let's say this vessel bursts at a pressure of 10 MPa. I also consider another example wherein for the same volume, let's say the volume is 1 meter cube, so that I don't need to carry the volume. I have the same 1 meter cubed vessel having a pressure of, let's say, the same pressure 10 MPa, ambient pressure is 0.1 MPa as earlier, but it contains, let us say, a refrigerant gas, and this refrigerant gas has a gamma, let's say, equal to 1.1. Now, I want to find out what is the energy released in the two cases. I just use my equation. We have derived this. E is equal to 10 MPa, that is 10 into 10 to the power 6 Pascal, minus 0.1 into 10 to the power 6 Pascal, that is P naught minus P ambient divided by gamma minus 1, and into the volume, which is 1, so much joules is what is generated over here. In this case, I have a similar expression. I have 10 into 10 to the power 6 Pascal minus 0.1 into 10 to the power 6 Pascal divided by, in this case, gamma minus 1 is equal to 1.4 minus 1. In this case, it is 1.1 minus 1 into volume, so much joules which is generated. Therefore, in this case, I take 10 to the power 6 outside. 10 minus 0.1 is 9.9 divided by 0.4 joules. And in this case, I have again 10 to the power 6 into 9.9 divided by 0.1. If I solve for this, I get a value of the energy release being something like 24.75 into 10 to the power 6. I can call it as megajoules. In this case, it's 99 megajoules. And therefore, you find, yeah, the energy released when I have something like a complex gas is very much higher for the same conditions compared to air. The question is, why should this happen? Why should an explosion of the gas at the same pressure, same initial conditions, same volume and same ambient conditions release much more energy? The thing is that a more complex gas, because of its different modes, different degrees of freedom, because of its structure, can hold much more internal energy. That means the initial internal energy of this gas is very much higher than the internal energy of this gas. And since we are talking of the drop in internal energy, well, the complex gas gives me much more energy. But why should the internal energy change and not the enthalpy? H is equal to U plus PV. It is this which decides the internal structure which holds the energy. This is just flow work which does not change substantially. Therefore, CV tends to be high for the complex gases, and since it has high, it holds much more energy. This is the logical conclusion. Having seen the values or having estimated the energy release in a rupture of a pressure vessel, let us go ahead and try to ask one more question. We said energy is liberated in the explosion of a pressure vessel, that is the rupture causes energy to be released. And it is this energy which creates a blast wave, and we will see the effectiveness of the energy release when we talk of TNT equivalence after some 3 classes. However, let us consider this energy release could be very slow, could be very fast. Whenever we talk of a constant volume explosion, well, it just goes with a bang. That means the energy release is very fast. Compared to a constant volume explosion, if I have something like a constant pressure explosion, what do you mean by a constant pressure explosion? Well, let's say, I have a piston which is driving the gas at constant pressure and the volume increases. Well, that could also provide some energy with which I could have an explosion taking place. And what is the value of the energy release? Let's say I have a constant pressure, therefore I have something like a piston pushing the gases at constant pressure, and let's say there is no change in the pressure of the gases. Let's say that the initial volume is V2 and the final volume is, let's say, V1. That means I am talking in terms of constant pressure into V2 minus V1 is the work done, which is the energy of the constant pressure process what we are talking of. If I were to consider this constant volume explosion derived from the thermal energy which is supplied to this particular volume, and also a constant pressure explosion by the thermal energy supplied for this particular change, is there something like this being more effective, this being more effective? I want to find out what is the conversion factor for the thermal energy into the energy, that is the mechanical energy obtained in the particular rupture. Therefore, let's do this particular problem. It gives us a feel of how much energy, how spontaneous energy takes place in a constant volume and the effectiveness of the explosion. And therefore, when I consider a constant pressure explosion, well, we say energy is equal to P into, we say it is equal to the V2 minus V1. And what is the heat which drives this particular explosion? The energy supplied is equal to Cp, that is the mass of the gas, into Cp into, I have T2 minus T1, or rather T1 minus T2, that is the heat, that is this is the final temperature minus the initial temperature. And I can write, well, Cp minus Cv is R, therefore Cp is equal to gamma R by gamma minus 1. Therefore, the heat which is supplied is equal to m gamma R T2 minus T1 divided by gamma minus 1. And now I do the same thing, mRT2 is equal to the value of pressure being constant, P into the final volume, let's say V2, minus I have Mr T1, the same pressure, into V1 divided by gamma minus 1. We have to take gamma into MRT is the P2 V2. I still have to retain this, or rather Q is equal to I have gamma divided by gamma minus 1 into I have P V2 minus P V1 divided P V, that is about it. That means I have gamma by gamma minus 1 into P into I have V2 minus V1. What is the work done? Work done is equal to P into V2 minus V1. This is P into V2 minus V1 into gamma minus 1. Therefore, if I take the ratio of the work or the energy which is released in the particular constant pressure process, let us say I have E, I say constant pressure process, divided by Q in a constant pressure process, I have P V2 minus P1, P V2 minus V1 cancelling, and I get E by Q is equal to gamma minus 1 divided by gamma. If I do the same thing for a constant volume explosion, we found that the energy released in the constant volume explosion is equal to V into gamma minus 1 into we had P, that is the P0 minus P1 or P ambient, and we also find that the energy heat which is supplied to do this, I can write it as equal to I have M CV into the T2 minus T1, which I can now write as equal to Mr divided by gamma minus 1 into T2 minus T1, again writing Mr T2 and Mr T1 as equal to P0V and P1V. I get this equal to V into P0 minus P1 divided by gamma minus 1, and therefore, for a constant volume energy release divided by constant volume thermal energy what is required is equal to V, same expression, therefore, it is equal to 1. Therefore, we find that since gamma is of the order of 1.4, the energy released in a constant pressure process is much lower, and we know that a constant pressure process is a slow process. Whereas, when I talk in terms of a constant volume explosion, it is a sudden process, and therefore, now I can plot as a function of time the value of, let us say, energy divided by the heat release. I say, well, for a sudden process I have this equal to 1, and as I move towards a constant pressure process, the value I get is gamma minus 1 divided by gamma. Therefore, the suddenness of an explosion is important to be able to convert all the thermal energy into the mechanical energy. This completes what we said is about the rupture of pressure vessels, about the energy release, and we find, yes, now we can estimate the energy release, but there is one small problem which very often the chemical industries face, and let us quickly go through it. The problem is like this. In any chemical plant or any plant, you have a series of reactors. You are trying to form some substance, like for instance, let's go through one particular example. Let's take the example of the explosion which happened at Flixborough in UK, wherein on June 1, 1974, there was a spillage of, let's say, cyclohexane which mixed with air and just ruined or made Flixborough into a ghost city. What happens in a chemical plant? You have somewhat like you have reactors, several reactors which are essentially storage vessels. You have, let's say, reactor 1, reactor 2 over here, I have reactor 3 over here. You have several of these reactors, and all these reactors are always connected by pipelines, because from one reactor I transport it to the second reactor, to the third reactor, to the fourth reactor, and so on. Now the question is, supposing by chance in one of the reactors there is an explosion. I don't want my entire plant to get damaged. I would like to still protect my second reactor and third reactor and somehow ensure that the explosion from reactor 1 does not get into reactor 2, Or rather, I am interested in so designing this pipeline which connects my different reactors should be such that let's say its diameter must be d and let's say its length must be L. I am interested in the connection having a particular diameter d and a length L such that explosion from one reactor does not get into this. Even if this explodes, can I still save this is the question. Therefore, we are looking at this particular connecting, or let's say the pipeline, and we immediately say, well, I have studied this. If d is less than the quenching dimension, or rather in the case of detonation, if d is less than the critical diameter, well, my problem is solved. Flame cannot travel. But the problem tends to be a little more complex. There are additional factors which are involved, and that is what I want to highlight now. Let's say, well, in the reactor, one, I want to simplify it, I want to put the scheme as, well, I show the reactor through some another geometry. Let's say I have one reactor in which there is some explosion taking place. Well, it's a donor as far as an explosion is concerned. It is connected to a next vessel which receives the explosion. I call it as a receptor. Well, I am interested what must be the diameter of this pipeline and what must be the length of this pipeline to make sure that the explosion does not travel from one particular reactor to the other. Therefore, now I tell myself, supposing, let us say, that the diameter of this particular connector is such that it is somewhat same as the surface area of this particular vessel, or rather, if I say volume and I say mean surface area, if the surface area, cross-sectional area of this vessel is same as something like, let's say this diameter is d, is same as, let's say, surface area corresponding to volume 1 is same as, let us say, pi by 4 into d square. Well, I have such a huge vent that maybe a flame gets started. Whenever gas is getting generated, it really cannot build up pressure here because the vent is so large that it just allows the gas to go through, and therefore in this case there is no danger at all. But to think in terms of a large vent, and why does it happen? The vent area is so large, that means before pressure with time tends to get built up, at the low pressure itself it starts venting the gases, and therefore you have something like a gas going over here, and therefore it is a unburned gas mixture which goes out. Even if it is burnt, if the diameter is less than quenching thickness, well, it quenches, nothing is going to happen, well, it's safe. But in practice it's not possible. In practice d, the diameter or the surface area is going to be very much smaller than this, and therefore since the vent area is much smaller than the original cross-sectional area, this happens like a constant volume vessel or a constant volume reactor which is exploding, and in a constant volume explosion the maximum value of pressure is Pm, which we have hydrocarbon, we said it's between 5.7 to something like 7 atmospheres. If it is hydrogen, it is of the order of 11 atmospheres, and therefore I have a constant pressure explosion which gives me a high value of Pm. And therefore what is going to happen? You have a high value of Pm, and therefore the gas comes in here, it comes at high pressure, and it expands into this receptor vehicle, that means let's say V2, as a hot jet. If this hot jet comes into this particular reactor over here, and if this hot jet immediately mixes with the cold reactive gas over here, or with the gases in this particular volume, what is going to happen? Well, this jet gets extinguished, and therefore it is not possible for you to initiate combustion over here. And since that means I am talking of, if the mixing of the jet with the gases here is very rapid, that means the mixing time, let's say Tm, is a very small number, well, I cannot ignite these gases because it gets quenched. However, if the hot jet comes and the chemical reactions occur so rapidly that heat is getting generated, well, this also explodes, or rather, if the chemical reaction time, let us say Tc, of the gases here is a small number, well, this container or reactor explodes. Therefore, we find the ratio of Tm by Tc. If the mixing time is small, well, I am safe. Therefore, for safety, I say, well, that mixing time divided by the chemical reaction time must be less than a particular value, and this also therefore becomes an important parameter. It is not only the quenching distance, and mind you, whenever we do these things, we also talked in terms of quenching distance divided by the flame thickness or critical tube diameter for a detonation. Let's concentrate on flame dq by Tf. We said is of the order of something like 5 or 10 or something of this order. We also were able to put the quenching diameter in terms of a Peclet number, that means the convection heat transfer divided by the conduction heat transfer. But it is very difficult to theoretically determine this particular diameter, and in practice what is done is we derive it from experiments, and the diameter so derived from experiments is known as maximum experimental safety gap. And it is known as MESG. It is derived for the different gases, and we know what must be the type of diameter what is used. It is also necessary that the length must at least be of this diameter, such that the heat losses and the active radicals lost to the walls will quench it. And in practice, we use the maximum experimental safety gap, but in addition to the safety gap, we must also look at the phenomenon by which things takes place, the relative size of this relative to this volume, the mixing times and chemical reactions times, in order to make sure that explosion in one vessel does not get into the other vessel. Well, this is all about explosions in the cryogenic vessels, rupture of pressure vessels, and also something on containment of explosions in a particular reactor and not spreading to the other. In the next class, what we do is we go to a slightly different topics. We have been restricting ourselves to gas phase and dust explosions. We will take a look at the condensed or the solid explosives in the next class. In the next 2 or 3 classes, we will deal with condensed explosives. Thank you. An announcement, please. The lectures between numbers 28 to 32 covered the different categories of explosions. The references for further reading on these lectures, namely those between lectures 28 to 32, and a set of homework problems pertaining to these specific lectures, are given in the downloads of this video course.